All right, welcome to radical functions and equations. So now that we've got it down that we have square roots of 5s and square roots of x's and all sorts of things, what starts happening when we put an equal sign in them? Well, we're going to start off with what they look like on a graph. And this is kind of crazy. You know, we did y equals 1 over x, g of x equals 1 over x minus 5, and we had some issues there. If you remember, let's write one of those up there. F of x equals 1 over x. When we had something like this, you remember there's a problem with a fraction where this cannot equal 0 on the bottom or we blow the fraction up and it gave us a vertical asymptote. That was kind of a fascinating little thing. Well, we're now running into a second problem. If we do something like f of x equals the square root of x, think about what numbers you can stick into a square root. Very nice stuff like square root of 25 gives you 5, and square root of 4 gives you 2, and square root of 1 gives you 1, square root of 0 gives you 0. And think about why all this works. 5 times 5 is 25, 2 times 2 is 4, 1 times 1 is 1, 0 times 0 is 0. But as soon as I do something like this, square root of negative 9, we don't have any numbers that times themselves. Some of you might think negative 3. What's negative 3 times negative 3? It's a positive 9. So that doesn't work. The square root of negatives don't work. If you are dealing with real numbers, and especially with graphs where you're on a real number x and y plot, then this is not an option. This thing has a restriction, and whatever is under the square root sign has to be greater than or equal to 0. You can only stick positives and the number 0 in there. This is a domain issue for functions. Remember, domain is anything that you can stick into a function, anything that can be on that first thing. For example, if we were to do an xy plot on the square root of x, you could call this f of x over here if you wanted. That would be all right. And stick in some of these numbers. So if we stick in 25 for x, what do we get for y? Well, the square root of 25 is 5. Stick in 4, we get 2. Stick in 1, we get 1. Stick in 0, we get 0. But as soon as you stick in negative numbers like negative 9, error. It doesn't come out to be a real number. And so we can't put it on the graph. So this becomes an issue and domain error. So anything below 0 is not in its domain. So what does this look like on the graph? Number one, when you can identify that the domain equals set of all x's such that x is greater than or equal to 0, that means only these numbers are going to be stuck in. Over here for this part of the graph, there's nothing there. So let's look. 0, 0 is right there. 1, 1 is going to be about right there. 2, 4, 2. Now notice I picked numbers that come out really nice. If you'd like to pick some weird numbers like a 7 and stick its decimal in there, that's okay. But what it will look like is kind of like this. Half of a U-shape type graph right here. So it actually comes in a little bit steeper there. There we go. And that's what they look like. All square roots will look like this. And so your goal in this graphing of these functions, we're going to stay very basic, and you need to find its domain. You got to find out what x's you can actually stick in and what you can't, and write that down. That'll be part of the instructions. Find the domain. And then actually stick in 2 or 3 points. Find the very limit of your domain so you know where the arrow starts, and then get a couple of numbers so you can kind of see where it heads off to. So let's try another one. Let's do g of x equals, let's do something like square root of x minus 3, and then let's add 5 to it. What'll happen here? So first of all, let's find the domain. Let's change colors while we're doing this answer here. So the domain is going to be where x minus 3 is greater than or equal to 0. This is important. These are the only numbers that can work to give us a graph, is if we make sure that underneath the square root sign, we're not taking the square roots of negatives. So this gives us a little math problem to solve, and we get x is greater than or equal to 3. So let's put the nice looking stuff around it. That now all says the domain equals the set of all numbers x such that x is greater than or equal to 3. So if we put this on a graph, 3 over here, 1, 2, 3, that is the beginning. There will not be a graph over here. We can only stick in these numbers to see what kind of a graph we get. So let's do our little x, g of x, or y over here, and see what happens. And let's try to stick in some good numbers. So we know that if we stick in like 2 or 1 or anything less than 3, we'll get an error. And you can try it. 2 minus 3 is a negative 1. Take the square root of negative 1. That's not a real number. You can't, what times itself would give you a negative 1? Doesn't work. Okay, so the first number in our domain is a 3. Let's stick in 3. We stick in 3 and we get 3 minus 3 is 0. Square root of 0 is 0 plus 5 is 5. So 3, 5 is the beginning of our cute little graph. Let's stick in something that'll come out nice if we can. Stick in a 4. 4 minus 3 is 1. Square root of 1 is 1 plus 5 is 6. Good. So we get 4, 6. Okay. What's the next good square root that'll come out? Square root of 4 would be nice. So 7. Let's stick in a 7. 7 minus 3 is 4. Square root of 4 is 2. 2 plus 5 is 7. So 7 is going to be one. And you can kind of see from there where we're headed. And we're going to get this shape again. It's kind of half of a U headed off to the right. Let's try one more. Get a different color again and do it. So let's try it right here. H of x equals, let's take 2 times the square root of x plus 7 and minus 1. There we go. Let's see what happens there. First of all, the domain. That's important. Take the domain, and it has to be where this guy inside, x plus 7, has to be a greater than or equal to 0. You have to only stick in for the square root numbers that will make it greater than or equal to 0. So subtract 7, we get x greater than or equal to negative 7. Now notice in this domain, the domain is going to be the set of all numbers x such that, let's make that look a little bit nicer here. The domain, let's give ourselves some more room, is going to be the set of all numbers x such that this happens. Yeah, most people just say, yeah, x is bigger than or equal to 7. All this is just making it look nicer. So that means we actually get to stick in negative numbers here, but when we add 7 to them, they'll turn into things we can take the square root of. So if we do x, y, well, that was a crazy looking y, huh? Let's do x, h of x. There we go. That's our y value right there. If we stick in, the very limit of our domain is negative 7. Let's stick that in to see what we get. Negative 7 plus 7 is 0. Square root of 0 is 0. 2 times 0 is 0. Minus 1 is a negative 1. So on our graph, negative 7, negative 1. That's where our little arrow is going to start, and it's going to head kind of this way somewhere. Let's put in a couple more points just to see where it goes. Negative 6. What will negative 6 do? Negative 6 plus 7 is a positive 1. See, even though we can stick in a negative number, when we added 7, it's good. That's why it's in the domain. Square root of 1 is 1 times 2 is 2 minus 1 is 1. So this one is going to be a little bit steeper. Here we always went up 1 and over 1. But here we're going over 1 but up 2. That's kind of interesting. Let's see, what's a good number that would help it work here? Maybe 2 plus 7 would give us a 9. Let's stick in a 2. 2 plus 7 is 9. Square root of 9 is 3. 2 times 3 is 6. Minus 1 is 5. So the point 2, 5. So yeah, you can tell it's just a little bit steeper, but that's what it looks like right there. Good. Let's give you a chance to do some of these graphs and find some domains on your own. To the boards! Here are some for you to try on your own. Write these down, pause the video, and give it a try. When you're ready to check your answer, let's see what happened. Press play. And welcome back. So we're going to graph this. First of all, we're going to find the domain. That's important. X minus 5 has to be greater than or equal to 0. I guess I should use a colon there. We're not, domain isn't equal to this inequality. This tells us, this little math problem, that x, add 5 over there, has to be greater than or equal to 5. So the domain is going to equal this set of numbers. We get to use anything that's bigger than 5. So 1, 2, 3, 4, 5. So we get to pick numbers that are right here, and that will work. And if we pick numbers over here, they won't. So if we do our little x, y plot or x, f of x plot, if we stick in like 4, nope, that's not going to happen. We don't get anything out. Try it. 4 minus 5, negative 1, square root of negative 1. So we stick in 5. That's the one we need. That's going to be the corner of our little arrow thing. 5 minus 5 is 0. Square root of 0 is 0. So 5, 0 is the point. Let's try 6. 6 minus 5 is 1. Square root of 1 is 1. Good. So 6, 1. And then we could do a 7. That's not going to be 9. 8, 9. 9 minus 5 is 4. Let's do that one. 9 minus 5 is 4. Square root of 4 is 2. And so we get 9, 2, probably somewhere around there. And there's our shape. There we go. Excellent. Nice job. Number 2. What happens when we do this one? G of x. Ooh, this is a big one. Look at that thing. First of all, let's get our domain so we know what numbers to stick in. We've got to make this guy right here. Yeah, that one right there. We've got to have him greater than or equal to 0. So let's write that. X plus 3 has to be greater than or equal to 0. Subtract 3 from both sides. X will have to be greater than negative 3, greater than or equal to negative 3, in order for this to be the numbers to come out with something that we can graph. Okay, we'll put this cute little thing on here. There we go. There's the domain. All right, let's do our little x, y plot. Call this guy g of x. And you'll notice sometimes I'll put a y, sometimes it'll be a g of x. They're the same thing. This just lets us know that the value that pops out when we stick in that x. All right, so we get, if we stick in negative 4, we're going to get a nope. So let's stick in negative 3 to start and like a negative 2. And then we'll see if we can find some others that come out nicely so we can graph them. Okay, so negative 3 sticks in there. We get negative 3 plus 3 is 0. 2 times 0 is 0. Minus 4 is a negative 4. So at negative 3, now remember that we can only stick in these numbers. So at negative 3, negative 4, looks like about down here, that's the beginning of our arrow. It's going to head off somewhere like that. So let's stick in negative 2 and see what we get. Negative 2 plus 3 is 1. Square root of 1 is 1. 2 times 1 is 2. Minus 4 is a negative 2. So we actually stuck in negative 2 in there like this. And this is how officially it would look. G of negative 2 is 2 times negative 2, square root of negative 2 plus 3 minus 4. So that would equal 2 times the square root of 1 minus 4 equals 2 times square root of 1 is 2 minus 4 equals a negative 2. So g of negative 2 is negative 2. And that's how it would look like that. All right, so negative 2 looks about right there. All right, okay. We need one more to kind of see where we are. Where's the next square root that would come out nice? We did the square root of 1, square root of 4. So if x is a 1, yes. So let's officially stick it in. G of 1 equals 2 times the square root of 1 plus 3 minus 4. That equals 2 times the square root of 4 minus 4. 2 times 2 minus 4 equals 4 minus 4 equals 0. Huh! Look at that. If we stick in 1, we get 0. So that's this point right here. So we can kind of see that we're headed off like that. And there's our graph with our domain. Nice job. Let's go look at the rest of radical equations. So now that we've started putting square roots in equations, how do we solve them? Something like, well, let's try it. If we had square root of x equals 5, we know how to solve this. We know what number goes in there. The square root of what number equals 5? Well, it's going to be 25. Let's go way, way back to the beginning. Do you remember this law of opposites? And that's exactly correct. We're appealing to this old principle that is eternal in nature. It will last forever, and it is always true, that whatever happens, there is a way to undo it. So here we have square root of x. What's the opposite of square rooting? Well, squaring is. So that's how we get rid of stuff. Square that side, and we get x equals 25. Ta-da! There we have it. It gets a little bit tougher when you start doing something like x minus 7 equals 9. Now you can't really tell exactly what happens, so how do we get rid of the square root? Square both sides, and we get x minus 7 here equals 81. Add 7 to both sides, x equals 88. And there we have our answer. For just a moment, we're going to take and see just how powerful this law of opposites is. The undoing of a square root is a square. Well, before we move on and catch some of the weird things that happen with squaring, notice this, that if we had the cube root of 3x plus 2 equals 4, something like that, how would we undo a cube root? Well, law of opposites says undo cube roots with cubes. So really, this could be cubing both sides, or fourthing both sides, or fifthing both sides, depending on what root we have. So the cube root, we cube both sides. There's a 3 there and a 3 there, and we now have 3x plus 2, because cube and cube root undid each other, equals 4 cubed, which is 64. Subtract 2, 3x equals 62, and divide by 3. We get divide by 3, divide by 3. Let's do one more just to make sure we got it. Cube root of 7x minus 2 equals 5. What would we do here? Cube both sides. To undo the cube root, gone, and we now have 7x minus 2 equals 125. Now when we add 2 to both sides, we get 7x equals 127. Divide by 7, divide by 7. Sometimes that comes out nice. On this one, it didn't happen to, 127/7. If you stick that back in, it'll work. So the special cases that we're going to go through with perfect squares are not necessary for perfect cubes. You actually get a free ride, just cube both sides and then solve it. Isn't that great? Okay, now we'll head back and talk about the word of caution for perfect squares. There is a word of caution here. Every once in a while, you'll get something that looks like this. Square root of x equals a negative 3. Now, we do have to say a word here, that square roots and squares undo each other most of the time. We're going to take a little step over here for a minute. We know that 5 squared is 25, and from that we get the square root of 25 is 5. But we also know that negative 5 squared is 25. So should the square root of 25 also be a negative 5? This is a debate that has happened amongst mathematicians for years and years and years and years. If you take the squaring function, it is actually a function. Every number squared goes to exactly one number. And that's great. It's a function. If we have the square root going back to square root of 25, going backwards and going to both the positive number that squares to it and the negative numbers that squares to it, it is no longer a function, which means your calculator can't punch out a specific answer. So there is an agreement among all mathematicians that in order for this symbol to represent a function, it always gives you the positive number. And it's kind of crucial. We just did a graph where the square root of x ended up looking like this. If it got both the positive and the negative one, it would end up looking like this. Well, is this a function? It isn't. So mathematicians, in effect, erased this portion of it and said, no, when we use this symbol, we are saying you take the positive one so we can always have one answer. Now, some of you may have run into a point where you saw this thing happen. If you haven't seen this, don't pay any attention to it, and we'll pick it up in chapter 8. But when you square root both sides, and you're like, but wait a second, square root of x squared, that gives us x is plus or minus 3. Yes, that is correct. Notice we have to put this symbol on here to get both numbers. When we just write the square root of 9, it means the number 3. So the square root, and this is called, some people call it the positive square root principle or the principal square root law, whatever. But square roots always designate, when you see this symbol, it is designated, even if you started with a negative number, the square root always gives you positive numbers, which is actually kind of interesting. It deals with the range, what comes out of a function. And for square roots, the range is always positive. So keep that in mind, that we can't get negative numbers out of it. It's an unusual little concept. We can't stick negative numbers into a square root, and we can't get negative numbers out of a square root. Square roots deal with positives. So right here, this one, you would love to stick 9 in there, right? But what is the square root of 9? 3. That doesn't work. Is there any number that will ever give us this thing? And the answer is no. There is no solution right here. And that may take a little bit of thinking and processing if you've run into this before. But the square root of a number, go ahead and stick it in your calculator, 9, will pop out a 3. It will not pop out a negative 3. So this means that sometimes when we're solving these solutions, we might end up with a bad answer. Let me show you what I mean. If you didn't recognize that this was a no solution, go ahead and square both sides. You're like, yeah, we can do that. X over here, negative 3 times negative 3 is 9, and you think 9's the answer. You must stick this back in here to see if it really works. And you get square root of 9 equals negative 3. What's the square root of 9? 3 equals negative 3. When we did this operation of squaring, the 3 and the negative 3 acted like the same number. The squaring took them both to a 9. And that's what happened. So we do have to be careful. So let's go ahead and stick this guy back up in here to make sure he's not an extraneous root. 88 minus 7 is 81. Square root of 81 is indeed 9. All right, let's try a few that are a little bit tougher now. All right, here's the next one. Square root of x plus 5 equals 11. Now you're like, oh, I want to get rid of that square root sign. Let's square both sides. Oh, we got to do this in a different color because this could be the death of your math life right here. You're going to square this side and you're going to square this side. Now, if you square this side and you want to say square root of x is now x and 5 is 25, you've just committed the cardinal sin of the freshman's dream. How embarrassing. You remember this plus sign? Yeah, that plus sign means you have to super distribute when you square both sides. You would have to do square root of x plus 5 times square root of x plus 5. And you get x plus 5 square roots of x plus 5 square roots of x plus 25 equals 121. Oh my word. Oops, I forgot that square root. And so you get x plus 10 square roots of x plus 25 equals 121. Do you see how we didn't really actually simplify this or get rid of the square root at all? It's possible we might have to do that in some problems, but really, first of all, let's erase this right here. And start this problem over with, let's get a square root by itself. Yeah, let's do that first and then look at what happens. So subtract 5, and we now have square root of x equals 6. Now when you square both sides, you get x equals 36. Let's double check that answer to make sure it works. Square root of 36 is 6 plus 5 is indeed 11. Oh, good. Let's try another one. It's a little bit like that. X plus 3 minus 4 equals 9. All right, so the first step is to get the square root by itself. So add 4 to both sides. And we get square root of x plus 3 equals 13. Now we can square both sides. and we get x plus 3, the square and the square root just undid each other. And what do we get here? 169. Oh, I like it. Now subtract 3 and we get x equals 166. And we can check that to make sure we didn't get an extraneous root. Square root of 166 plus 3, that's 169. Square root of 169 is 13. Minus 4 is indeed 9. All right, here we have it. The square root of x plus 6 equals x. This is going to be a little bit tougher because the x happens in both places, and they are not like terms. You can't solve it just, this is going to be a little bit tougher. So let's get the square root by itself. So subtract 6, subtract 6. Square root of x equals x minus 6. Square both sides, and this gets rid of that square root. But notice what happened over here. Square root of x squared is x. Good. Over here, don't you dare do x squared plus 36. That's a freshman's dream. You've got to FOIL. You've got to super distribute. This is polynomials. This is x squared minus 12x plus 36. You got to write that out side by side and distribute. All right, this is now a polynomial equation. Yeah, how did we do that? We get it equal to 0. Yeah, and so we have 0 equals x squared minus 13x plus 36. We factor it. This is a trinomial leading coefficient 1. So we've got to find the numbers that times to 36, which are 1 and 36, 2 and 18, 3 and 12, 4 and 9, 6 and 6, and those are they right there. X minus 4, better do negatives here, minus 4 and minus 9 are what give us 36, adding to negative 13. Excellent. So this gives us set each piece equal to 0, x minus 4 equals 0, gives us x equals 4, and this one, x minus 9 equals 0, x equals 9. Now, you remember what happened right here with the extraneous solutions. It's possible that in this squaring thing, we picked up an answer that doesn't work. So we're going to try this, and we've got to stick this guy back up here for both x's to make sure this works. So let's stick it in with the 9, and we get the square root of 9 plus 6 equals 9. Square root of 9 is 3 plus 6 equals 9. True. This is an answer. Let's try 4. Square root of 4 plus 6 equals 4. Square root of 4 is 2 plus 6 equals 4. Is that a true statement? It is not a true statement. Some of you may think, but we did it all right. How did we get a wrong answer? At this moment, if you were to think that it could be a negative, look how that makes it work. Yeah, if this would have been a negative 2 squared, it still would have ended up with 4 here. And so that's what caused it to pick up that extra solution that wasn't actually a solution. So 4 is not an answer, 9 is an answer. One more before we let you try some on your own. You may end up with 2 different square roots right around there. So if we had something like the square root of x plus the square root of x plus 7, and that one equaled 7. Ooh, doesn't that look horrible? It is possible that you will, let's isolate this guy away from everything else we've done, that you can't get both of these square roots by themselves. Here we were able to isolate the square root by itself, and here you have to, unfortunately, focus on one square root at a time. So I'm going to focus on this one. He looks ugliest, so I'm going to get him alone. Square root of x minus the square root of x. And so I have square root of x plus 7 equals 7 minus the square root of x. Yeah, and now you're going to be just a little upset at me, but I hope not too much. Let's square both sides and square both sides. And notice that on this side over here, we're left with x plus 7. So that's nice. That just, the square root and the squared, we got rid of one. But over on the other side, notice we have 49 minus 14 square roots of x. You may have to do that out on its own. It's 49 minus 7 square roots of x minus 7 square roots of x, and then plus square root of x times square root of x is an x. So this guy right here is exactly what I was telling you was terrible about squaring both sides on there. And I mentioned, you may have to do it in some problems, actually FOIL it out with a square root. You have now come to that time in your life. We had to. We didn't have any other option. We had to get rid of this square root, and now we can focus on the next one. So we now need to go back up here and get square root by itself again. So we're going to subtract 49 from both sides. There we go, minus 49, minus 49. And notice we can subtract this x off and subtract this x off. So now we have what's left. That's just a minus 42 equals a negative 14 square roots of x. Will this give us a fraction if we divide this off? Oh, I don't think so. So negative 14, and we get 3 equals square root of x. Oh, that was way too easy. Square root is by itself, square both sides. Square both sides, and we get x equals 9. Okay, let's see if anywhere we did it twice. We squared both sides twice. We could have picked up a bad answer, extraneous solution. So let's stick this back up in for x into the very original equation, and let's see if it works. Square root of 9 plus square root of 9 plus 7 equals 7. Square root of 9 is 3 plus square root of 16 is 4. It does equal 7. That's our answer. Great. Now you're prepared. Go try some on your own. To the boards! Here's some to write down. Go ahead and put them in your video notebook. Pause the video, work them out. See how well you can do with them, and then play when you're ready to see them worked out. Okay, here's with these 4 problems. This one's going to be the ugly one. Let's start with number 1. Subtract 5 to get the square root by itself, and we get square root of x minus 4 equals 6. Now it's by itself. We can undo the square root by squaring, and we get x minus 4 equals 36. Add 4 and we get x equals 40. Let's double check that answer back up here. 40 minus 4 is 36. Square root of 36 is 6 plus 5 is 11. That is indeed an answer. No extraneous solutions picked up in that process. Okay, so number 2, square root of x minus 2 equals negative 7. Some of you will see right away, wait a second, square roots can't produce a negative answer. This is going to be no solution. But in case you didn't see that, we're going to do this the long way. Square, and we get x minus 2 equals negative 7 times negative 7 is 49. Add 2 over, and we get x equals 51. Let's stick this back up in here and see what we get. Square root of 51 minus 2 equals negative 7. Square root of 49 is 7. Does that equal a negative 7? It does not. We picked up an extraneous solution. No solution to this problem right here. Excellent. All right, the next one. We now have, okay, square root is by itself, so we can immediately start off squaring both sides. We get x plus 5 equals x squared minus 30x plus 225. Again, freshman's dream, you may not just pass this squared, this exponent, across a plus or a minus sign. We are now in a polynomial equation, so we must get it equal to 0, subtract x from both sides, and subtract 5 from both sides. So we get x squared minus 31x plus 220. Oh boy. All right, we got to look at 220. This may take a little while. 220, we get 1 and 220, 2 and 110, 3 and, nope, 3 doesn't work, 4 and 55, 6, nope, 7, no, 8, no, 9, oh wait, 5 does work, 5, I'm sorry, I skipped 5. 5 would be 44. And you can see what's going on. We have a 5 and a 4 and an 11 going on, and so the next one up is going to be an 11 times 20. Yeah, that's right, that's right. So 11 times 20, oh, yep, that's our baby right there. Negative 11 and negative 20, This is going to break up to the negative 11 and the negative 20. Oh, good. Whew. Glad we were able to find that. I wasn't sure what was going to add to that 31. Okay, so it's now factored equal to 0. Each piece equals 0. X minus 11 equals 0. X equals 11. And x minus 20 equals 0. X would equal 20. Oh, what are the chances that both of them are safe? Let's try it. So let's stick 11 up in here, and we get square root of 11 plus 5 equals 11 minus 15. I think you can see where we're going to run into a problem. Square root of 11 plus 5, that's square root of 16, equals negative 4. 4 equals negative 4. Yep, does not work. 11 was an extraneous solution. And so let's try this one. 20 going in there, square root of 20 plus 5 is 25 equals 20 minus 5 is 5. Yep, we're going to get 5 equals 5. That turns out to be a nice one. Good, good. Okay, the final one down here looks to be one of the ugly ones. Sorry about that. Didn't mean to offend, but let's try to isolate this square root and take care of this one first. There we go. So we get square root of x plus 5 equals 1 plus the square root of x. When we square both sides, we have to do, unfortunately, just like over here, we must FOIL if there's a plus sign in there. We have to multiply it out. So on this side, we just get an x plus 5. Some of you may wonder why we don't actually do x squared plus 5x. We're not actually, this squared and this square root just cancel each other out. So over here, unfortunately, we can't just take the squared to just this little piece. So we get 1 plus 2 square roots of x plus x. And that may take some thinking. If you're not able to see where that comes from, put it over here and do 1 plus the square root of x plus the square root of x, which you add in the middle, and then square root of x times square root of x is x. Good. All right. So we've got to go back and isolate this square root now. We got rid of 1, now we've got to get rid of the other one. So subtract 1 from both sides and subtract x from both sides. Oh, it came apart. Oh, how nice. So this is 4 equals 2 square roots of x. Divide both sides by 2 and we get square root of x equals 2. Oh, this was too easy. We got x equals 4. But did we pick up an extraneous root? Let's stick it back up here, and there, and let's see what we get. Square root of 4 plus 5 minus the square root of 4. Does that really equal 1? Square root of 4 plus 5, square root of 9 is 3, minus 2 equals 1. You know, after something like this, I look at these big ugly problems and realize that the x's that were hidden the whole time were simple little numbers like 4, 3, 2, and 1. That's just amazing sometimes, right? Alrighty, now you're ready to head on to your homework.